We've now been introduced to the concept of the derivative, a powerful way to measure how one quantity changes in relation to another. Only problem is, actually calculating it is kind of tedious. But maybe we can figure out a better way to do it. It's difficult these days to imagine a world without computers everywhere. They become such a fundamental part of our everyday lives. Now, you might wonder, what does it take to be a good computer programmer? Well, in his book Programming Perl, affectionately known as the Camel Book, Larry Wall, the inventor of the Perl programming language, claims that the three great virtues of a programmer are, and I quote, laziness, impatience, and hubris. Laziness because you want to spend less energy solving problems, impatience because you want to spend less time solving problems, and hubris because you want to be the best at solving problems. Now, if you ask me, those same three qualities, in moderation of course, are also the qualities of a great mathematician. We like to find efficient and elegant ways of doing things that would normally take a lot of work. And from what we've seen so far with calculating derivatives, yeah, that's a lot of work. Looking at the ratios between changes of variables as those changes get smaller and smaller and smaller, and trying to figure out what value that ratio is settling in on. So in well-deserved frustration, we might ask, how can we efficiently find derivatives of various functions? After all, our natural tendency as humans is to look for patterns and shortcuts. How can we put that pattern hunting sense to use here? Well, to start off with, we might look at a few simple cases. We said the derivative is supposed to be the slope of a curve, and we already know how to find the slope of a line. Rise over run gives us the slope between any 2 points on a line, even if those 2 points are very close together. So it would make logical sense if the derivative, the slope at a single point, was the same as the overall slope of the line. So we'll agree that the derivative of a linear function, mx plus b, is just the slope, m, of the line. Now, another thing we often do as mathematicians is to look for special cases where interesting things happen. One special case here might be, what if the line has a slope of 0? Well, that would make it a horizontal line, which is a constant function. No matter what x is, the y value always comes out the same. Also, notice we don't even have to write 0x plus b here, we can just write b. And if you look at that, now we have a new rule for derivatives. The derivative, that is the slope, of a constant, a number, comes out to 0. If we have a function that no matter what we plug in, we always get the same value, say 5, and then we ask how sensitive is that function to change, well, it's not sensitive at all. It's a constant function, so it doesn't change. 5 will just always be 5. So what other functions can we find derivatives of? There's a lot to choose from. Well, one possible place to start might be power functions. X raised to some power, like x squared, x cubed, and so on. How could we tackle those? Well, I think this is a great time to use another tool we have at our disposal, one that all too often gets a bad rap in math class: technology. Computers, certain calculators, even the cell phone in your pocket, or in your hand. They're all good at calculating derivatives. And that frees up precious brain power to use for more important things, like understanding what derivatives mean and using them for problem solving. And you don't even need an expensive, clunky graphing calculator either. If you have an internet connection, which I assume you do if you're watching this video, then there's a web-based graphing calculator that's not only easier to use, but completely free: Desmos. If you go to desmos.com, you have what I would say is currently the best tool for visually understanding mathematics. You just type stuff in and it works. Let's go ahead and open it up. Say we want to look at the graph of f of x equals x squared. We can just directly type it in, and voila, we have the parabola that's the graph of our function. Let's find some derivatives. If we type in f prime of 1, Desmos automatically picks two very, very close together points that are close to x equals 1, plugs them into the function, and finds the slope between the 2 points, and tells us that the slope is 2. If we change that to f prime of 2, it does the same thing, but this time close to x equals 2, and then we get a slope of 4. F prime of 3 is 6, f prime of 4 is 8, and at this point you're probably starting to notice a pattern. Whatever number we plug in, the derivative seems to be double that number. We can do even better. If we change that to f prime of x, then it plugs in all possible inputs to our window, and it shows us a graph of the entire derivative. Here it's blue. Wouldn't you know it, we've got a line that has a slope of 2 and a y-intercept of 0. That would be y equals 2x. And if we verify that by typing in y equals 2x on the next line, there we go. The line we get perfectly matches the derivative. So that tells us that the derivative of x squared is indeed 2x. Here's another way to think about that. If we go ahead and just focus on that parabola, then it starts off sloping downward with a negative slope. It gets more and more shallow until the slope is 0 at the bottom, and then the slope gets more and more positive. And that's exactly what the graph of y equals 2x does. Starts negative, goes to 0, and then gets more and more positive. So, in other words, the derivative, 2x, tells us the slope at any point of that parabola. Excellent. Now, what if we change our function to x cubed? Well, all we need to do is change the function in place to x cubed, and now the blue graph, which is the derivative, seems to be a parabola. So maybe the derivative of x cubed is actually x squared. Well, let's try it out. If we type in y equals x squared, then no, it's not quite right. The parabola is too low. But if we multiply it by something, we might be able to get it to be a little steeper. So we could try y equals 2x squared. Not quite, but close. Maybe 3x squared. Okay, that works. So the derivative of x cubed is 3x squared. And what that means is that if I want to find the slope of the graph of y equals x cubed at any point, I would just calculate 3x squared. And that's the slope of x cubed. Awesome, let's keep going. What about the derivative of x to the 4th? Let's go ahead and change it, and this time the blue graph, the derivative, is a cubic graph. So my hunch tells me that the derivative of x to the 4th is going to be x cubed times, again, some number to get it to match. So let's see what we can do. 2x cubed, not quite. 3x cubed, close, but not quite. You can still tell there's a little change here. Maybe 4x cubed? There we go. Now it matches. So the derivative of x to the 4th power is in fact 4x cubed. Hold up. Do you feel that? That gut feeling you get when you start to notice a pattern forming? Okay, maybe that's just me. Anyway, it seems that the coefficient always matches the original exponent, and that the new exponent is always one less. And it turns out that that pattern continues, which is where we get our first big derivative shortcut from, the power rule, which says that to differentiate a power function, that is, x raised to some number, all we need to do is bring the exponent down in front to multiply, and then decrease the exponent by 1. And then by finding this pattern, we can now find the slope of a whole class of power functions. Now, I want to point one thing out. To be fair, we haven't actually proven the power rule. We don't really have the tools to do so yet, but we can at least use it. Think of it like your car. You don't need to know how it was built in order to learn how to drive. But later, once you have a good feel for it, it's eventually a good idea to look under the hood and see why everything works, which we'll also do here soon, I promise. There's another couple of simple rules for derivatives that we can figure out by thinking of them as rates of change. Say we have a tank of water. We turn on a faucet that pours water into the tank at a rate of 3 gallons per minute. Then we turn on another faucet that pours water into the same tank at a rate of 5 gallons per minute. It seems reasonable that the amount of water in the tank is now increasing at a rate of 8 gallons per minute. We should just be able to add the two rates. That makes intuitive sense. So that is the basic principle behind the sum and difference rules. Those basically say that if we have two functions added together or subtracted from each other, and we want to find the derivative of the sum or difference, all we need to do is add or subtract the derivatives of the individual functions. Let's take a look at the tank again. Say we have not one, but 3 identical faucets, and each of them is pouring water at a rate of 4 gallons per minute. Well, now it seems reasonable to say that the amount of water in the tank is increasing at a rate of 12 gallons per minute. 3 times the number of faucets means 3 times the rate that water comes out. Now that's the idea behind the constant multiple rule. That one says that if we want the derivative of a constant multiple of a function, that is, a function times a number, then we just multiply the derivative of that function by that same number. So armed with the sum and difference rules and the constant multiple rule, we can upgrade from derivatives of power functions to derivatives of entire polynomials. Remember the basketball example from last lesson? Let's use what we've just learned to find the derivative of the height function. We basically just take it step by step. The derivative of 5, a constant, is 0. The derivative of 20t, a linear function, is 20. What about the derivative of 16t squared? Well, the derivative of t squared on its own would just be 2t, so by the constant multiple rule, the derivative of 16t squared is 16 times 2t. Clean things up a little bit, and we find that the derivative comes out to 20 minus 32t. Now we wanted to find the derivative at t equals 1 second. So all we need to do is just plug in 1 for t. And you find that just like last time, that the basketball is descending at a rate of -12 feet per second, in case you forgot. Okay, that was way easier than tediously finding the slope over smaller and smaller and smaller intervals. We got the answer instantly. That's the power of patterns. Okay, what about all the other functions? Exponential functions, logarithmic functions, trigonometric functions. How do we find the derivatives of those? Each one is found in all sorts of real-world models, so they have to be important. Well, each one can be tackled in a similar way, making use of technology, examining the graphs, and looking for patterns to try to figure out their derivatives. We'll be doing exactly that in class, though I suppose there's nothing stopping you from doing it yourself. You don't need me to tell you to play with math. Over the next few lessons, we'll be developing tools that'll help us find derivatives for more and more types of functions, until we can use them to look at the most sophisticated real-world models and how they react to change.